Here's a thought experiment. You're running a PostgreSQL database with a search index and a Redis cache alongside it. Every time a user updates their profile, you need to update all three: the database, the search index, and the cache. So you write to all three simultaneously. This is called a dual write. Now here's the problem nobody warns you about. Two clients concurrently update the same record. Client 1 wants to set value x to y, client 2 wants to set it to b due to timing. The database sees client 1's write first, then client 2's, so the database ends up with b. But the search index sees client 2's write first, then client 1's, so the search index ends up with a. No error occurred. No exception was thrown. Both writes succeeded. But the database and search index are now permanently inconsistent, and you'll never know. The solution Kleppmann proposes is counterintuitive. Stop trying to write to multiple systems simultaneously. Instead, write to exactly one in the database and let the event stream do the rest. This works because databases are already event streams in disguise. A replication log, the write-ahead log that a database leader sends to its followers, is literally a stream of database write events. Every insert, update, delete is an event. Followers apply those events to build their own copies of the data. The state machine replication principle makes this precise. If every replica processes the same events in the same order, they all end up in the same final state. That's not just a database concept, it's a streaming concept. So the connection between databases and streams runs deeper than it first appears. It's not that databases use logs for performance. It's that a database fundamentally is a materialized view over an event stream. Once you see that, change data capture becomes obvious. Change data capture, or CDC, is the process of observing every write to a database and publishing those changes as an event stream. Instead of dual writing to your database and search index simultaneously, you write only to the database. The CDC system taps into the database's replication log and publishes each change as an event. The search index, the cache, the data warehouse, they all become consumers of that change stream. They stay in sync automatically, always in the same order the database saw the writes. This approach elegantly solves the dual write consistency problem. The database becomes the single leader. All derived systems become followers. Just like database replication, but for heterogeneous systems. LinkedIn built Databus for this purpose. Facebook built Wormhole. Yahoo built Sherpa. For the open source ecosystem, Bottled Water and Maxwell decode PostgreSQL's write-ahead log. Debezium does the same for MySQL by parsing the bin log. MongoDB reads MongoDB's oplog. Golden Gate provides similar facilities for Oracle. Kafka Connect integrates all these CDC tools into a unified pipeline feeding Kafka. A few implementation details matter. First, CDC is asynchronous. The database does not wait for the change to propagate to consumers before committing. This means replication lag applies. Consumers may be slightly behind. Second, if you truncate the log and add a new derived system, you need a consistent snapshot, a full copy of the current state taken at a known offset, before applying changes. Third, log compaction can help. Kafka retains only the most recent write for each key, so a new consumer can rebuild the entire current state by scanning the compacted log from offset 0. The key insight: instead of solving the distributed consistency problem across multiple systems, you make one system the authoritative source of truth and stream its changes to all others. Change data capture operates at the database level. It captures low-level mutations: row updated, record deleted, index entry changed. The application doesn't know CDC is happening. It just writes to the database normally. Event sourcing operates at the application level. Instead of storing the current state of the application, you store the immutable log of events that led to current state. Events are high-level domain facts: student enrolled in course, user cancelled subscription, payment declined. The application is explicitly built around an append-only event log. Updates and deletes are discouraged. Instead, you append a new event. Why does this distinction matter? Consider storing one entry was deleted from the enrollments table and one cancellation reason was added to the student feedback table versus storing student cancelled their course enrollment. The first is a low-level mutation. The second is a meaningful business fact. If you later introduce a feature, say, offering the cancelled seat to the next person on the waitlist, the event-sourced version makes it trivial to chain that new behavior off the existing event. The mutation-based version requires reverse engineering intent from structural changes. The current state is derived from the event log by replaying events from the beginning or from the last snapshot if you've stored one for performance. This gives you complete auditability, easy debugging, and the ability to derive multiple different read-optimized views from the same event log. The analogy: accountants have used this approach for centuries. When a mistake is made, they don't erase the incorrect entry, they add a correcting entry. The ledger is an append-only log. Here's a concept from Pat Helland that captures this beautifully. The database is a cache of a subset of the log. The mutable state you query is just a materialized projection of the immutable event history. The log is the truth. The database is the cache. State, streams, and immutability are three facets of the same idea. State is the integral of events over time. An event stream is the derivative of state over time. Keeping the log gives you the ability to derive any view, past or future.